The first thing we're going to look at in this chapter is how to balance a nuclear reaction. And they're not too hard to balance, all right? I find them kind of fun, but again, I'm a chemist and I like Star Trek, so make your own conclusions. However, the punchline of balancing a nuclear reaction is that the number of reactant protons has to equal the number of product protons. And the same thing for the neutrons. The number of reactant neutrons must equal the number of product neutrons. All right, so this is kind of interesting. It's kind of like law of mass action, but with a little bit of twist, as we'll see. So here's an example of a balanced nuclear reaction. This is a reaction between a radium isotope. It's radium-226 on the left-hand side. And if you look on the periodic table, radium is number 88. Well, radium-226 decomposes into an alpha particle, which is 4,2 helium. You could have written that as 4,2 alpha. That would have been fine. In addition to the alpha particle, it's also a radon emitter. It's a radon-222. If you look on the periodic table, radon, symbol Rn, is number 86. Anyway, this is a balanced reaction because the lower left-hand numbers, which are the proton numbers, are 88 equals 2 plus 86. All right, no problem. And the upper numbers, which are mass numbers, which are technically protons plus neutrons, but that's a way to confirm that the neutrons are the same on both sides. So 226 on the left equals 4 plus 222. If those numbers for both mass numbers and atomic numbers are balanced, you have a balanced nuclear reaction. So this is a kind of problem you might see. Uranium-235 is the active component of uranium samples. And a lot of times when people wish to make nuclear power or nuclear bombs, they want the uranium-235, not the more abundant uranium-238. But anyway, uranium-235 decomposes through beta decay to a new product. Let's find the identity of the new product. All right. Now, beta decay just means that a beta particle is emitted. And since uranium has 92 protons and it's uranium-235, you can write the symbol like that. So uranium-92 on the bottom lower left, 235 in the upper left. If you have, as I said, a beta decay, that means that a beta particle is going to be a product. And this is something we'll see. If you see that something is decaying or is undergoing an emission, whatever is decaying or undergoing the emission will be a product. So these would be beta decay reactions or a beta emission reaction, same thing. It just means that a beta particle is going to be a product. And if you look back on that list, beta particle is like the supercharged electron. It has a 0 minus 1 e. And yes, you could write 0 minus 1 beta, and that would be fantastic. So in this problem, we don't know what the mystery product is, this thing right here. But we can figure that out easily by remembering that protons have to equal each other on both sides, and the mass numbers, which means neutrons, must also equal each other on both sides. So you can probably see the math isn't too crazy here. The top part, 235 equals 0 plus A. You can solve for A. On the bottom part, 92 equals negative 1 plus Z, and you can solve for Z. So let's do the easiest one. 235 equals 0 plus A, so that's no-brainer. A, 235. Woohoo! The bottom one, 92 equals minus 1 plus Z. So Z equals 92 plus 1. Put the negative 1 on the other side. Z is 93. So you put this all together and look on the periodic table to see that Z93 is Neptunium, Np. So the balance reaction here, uranium-235 on the left, a beta particle on the right, plus Neptunium-235. All right, so no big deal. A periodic table, of course, will be helpful. If you don't know that 93 is Neptunium, which is quite all right, you can absolutely look that kind of stuff up to figure it out. The inner reaction here is worth talking about. Inside the uranium-235, what's really happening is a neutron is breaking down into a beta particle plus a proton. And you can see now maybe why beta particles are listed as they are. Beta particles 0 minus 1 e plus a proton, which has the symbol 11p. You can see that on the right, you've got 1 and 0 0 on the top, so you'd have a 1 on the left. And on the bottom right, you've got -1 plus 1. That goes to 0. That's a 0. So a neutron in uranium-235 is breaking down to a beta particle plus a proton. It makes your uranium go to neptunium. It's going up in atomic number, even though the mass number stays the same. And that's kind of a fascinating thing. Neptunium has one more proton, but technically one less neutron than uranium-235 does. This is something that's kind of interesting. A lot of these nuclear reactions, the neutrons will break down into an electron plus a proton. If you remember from Chem 221, we said that the neutron was the most massive of the three particles. Protons were close, but a little less, and electrons were really small. Well, a proton plus an electron essentially equals the mass of a neutron, and the +1 proton and the -1 electron will combine to make something neutral. Whoa. Anyway, this area is pretty trippy, as you can probably see. Here's another reaction. We've got a uranium-235 on the left. This time it's breaking down to a thorium-231 plus a mystery particle. Well, the question is, what is the unknown particle? And again, what you can do is use the fact that the protons have to equal each other on both sides, and the neutron/mass numbers must also equal each other on both sides. So let's do the Z of the mystery particle first. 92 equals 90 plus Z. So subtract 90 from both sides. You're going to see that Z here is a 2. And let's do the mass numbers now. On the top, 235 equals 231 plus A. So subtract 231 from both sides. You're going to see that A there is 4. And if you remember from the list of particles before, something with a 4 and a 2, well, automatically the 2 would mean that you'd have a helium for X, or you could write, of course, alpha. 4, 2 is the symbol for alpha. So let me get rid of my little funky stuff there. There we go. Now you can see clearly without my graffiti that yes, we do have an alpha particle, which has the symbol 4,2 helium or 4,2 alpha. All right. So again, knowing what those names mean in terms of a formula there will be helpful as you go through it. This one, you have to know that 4,2 helium is an alpha particle, et cetera, et cetera. Emission and decay, like we talked about earlier, imply that something is being created, i.e. it's a product particle, and there's quite a few examples of this when it comes to these reactions. This is an example of a positron emission. Now, positron has the symbol 0 plus 1 beta or 0 plus 1 e, either way is fine. So because it's a product, we would say this positron is being emitted, or you could say it's a positron decay. Either one is fine. This is a polonium-207 undergoing positron emission to a bismuth-207 nucleus, which is kind of interesting. Sometimes you'll hear the term capture, and just like emission and decay imply a product particle, capture implies that something is a reactant. And a real common example of this is what they refer to as neutron capture. So in a neutron capture reaction, there's going to be a neutron as a reactant. The neutron is 10N, so this is an example of a fluorine-19 undergoing neutron capture to become fluorine-20. And again, you can figure out what the missing particle is because reactant protons equal product protons, and reactant mass numbers equal product mass numbers, et cetera, et cetera. You'll see different kinds of particles and decays and emissions and captures and stuff, but just remember, capture means reactant, while decay or emission means that that missing piece is going to be a product. Now, positrons and antimatter are really interesting. Paul Dirac was the one who, in Chem 221, we talked about briefly. He took relativity and applied it to quantum mechanics, so the m sub s spin quantum number popped out. But anyway, he was actually the first one to predict that antimatter could be a real substance, and it was 1928. And the antimatter is identical to regular matter, except it has like the opposite charge. So down here in yellow is an example of a positron reaction when it reacts with an electron. And anytime you have matter with antimatter, in this case it would be an electron with an anti-electron, you can see what happens. The lower left-hand numbers cancel out and go to 0, and the upper left-hand values also cancel out and go to 0. So in this case, a positron and an and a regular electron, they just combine to make gamma rays. This is called an annihilation reaction because the matter is totally turned into energy. We'll talk about that more later. If you have two particles coming together, you create two gamma rays. There's different kinds of rules and this level that while number of particles equal number of rays, don't worry about that. But this is actually something that's very useful. So in addition to sci-fi geeks like myself getting all excited here, this annihilation reaction is actually used in what's called positron emission tomography, PET, and that's a medical facility that's used, for example, at OHSU, stuff like that. Lots of examples of annihilation reactions. This is an example of what's a neutrino and an antineutrino coming together. And again, those are also types of these subatomic particles. We won't talk about those as much, but anyway, they do come together, creating gamma radiation. Pretty crazy. Neutrino was also something that was first postulated by Pauli. Pauli exclusion principle was another thing from Chem 221, where every electron has its own set of 4 quantum numbers. He was the one that predicted the neutrino, and neutrino detection is an active area of research even today.